All right, let's dive in. Today we are pulling back the curtain on mathematics itself. And don't worry, we're not here to solve a bunch of equations. Instead, we're going to explore the fundamental rules, the very bedrock, that prevent the entire system from collapsing into a kind of logical black hole. So, let me ask you a question. Imagine you're making a playlist, but it's the playlist of the greatest playlists of all time. It's the ultimate collection, right? Now here's the real brain twister. Can that playlist include itself as one of the tracks? This isn't just a fun little riddle, you know. This exact kind of self-referencing question reveals a deep and frankly dangerous paradox that mathematicians absolutely had to solve to protect the very foundations of logic. You see, this simple act of grouping things together, whether it's songs into a playlist or numbers into a category, it has a formal name. It's called set theory, and you can think of it as the foundational language that pretty much all of modern mathematics is written in. And just like any language, it needs some clear grammar rules. So, before we can even start grouping things, we need a really basic rule for identity. How do we know for sure if two collections, or in math terms, two sets, are actually the same thing? Well, the first big rule is called the principle of extensionality, and it's actually wonderfully simple. All it says is that a set is defined only by what's inside it. That's it. So if we go back to our playlist analogy, this means that the order of the songs doesn't matter. And repeating a song, that doesn't create a new playlist. The identity of the set is based purely on the unique members inside it.
So look at this. Playlist A and Playlist B have the exact same songs, just in a different order. According to this principle, they are one and the same. They are identical. The content is all that matters. Pretty straightforward, right? Well, maybe not.
It turns out this very simple, very logical rule has a hidden loophole, a really bizarre and dangerous one that can cause the entire system of logic to just loop back on itself, creating a total paradox. Now, there's a technical term for this self-referential loop. It's called impredictivity. It's what happens when you try to define something by referring to a group that includes the very thing you're defining. You know, like our playlist of all playlists trying to list itself as one of its own members. And this reveals a really crucial point. If a set is defined only by its contents, then the definition of the set has to come after its contents are already established. The collection can't logically be one of its own components. It's like saying a finished car can't also be one of the bolts used to build it. And mathematicians knew this was a massive problem. The source material for this explainer calls it, and I love this phrase, the usual vicious circle in the form of the notorious impredictivity. You can just feel the academic frustration in that phrasing, can't you? A vicious circle right at the heart of logic is, well, it's not something you want.
So how do you fix a paradox this fundamental? I mean, you can't just ignore it. You have to introduce a new explicit rule to slam that loophole shut for good. And that rule is called the element axiom. So, what is this thing? The element axiom is what our source calls a hard axiom. It doesn't replace the original rule, it just supplements it. It takes what extensionality only implies, the idea that a set has to be separate from its members, and it makes it an explicit, unavoidable law. And what's wild is that this crucial fix is actually missing from a lot of standard mathematical frameworks. Okay, here is the absolute core of the fix. Extensionality implies that a set should be distinct from its members. It's kind of a suggestion baked into the logic. But the element axiom enforces it. It changes the rule from a should to a cannot. A set cannot coincide with any of its members, period. The loophole is now officially and permanently closed.
But you might be wondering, why does this matter so much? It seems like such a small technical clarification. How does adding just one extra line of code to the operating system of math really create a more robust foundation? Well, it matters because, as the source points out, that crucial implication is not clearly visible from the axiom itself. Without the element axiom, that rule against self-containment is basically open to interpretation. It's a suggestion, not a law. And let me tell you, when you are building the logical foundation for all of science and engineering, you cannot build it on suggestions. This whole debate actually gets pretty deep into the philosophy of math. You've basically got two camps. The Platonists, they believe sets are real, abstract objects. So for them, of course a set can't contain itself. It's just understood. But then you have the nominalists, who see a set as just a name for a multiplicity of things. For them, that rule absolutely has to be spelled out. The beauty of the element axiom is that it makes the system work purely formally, no matter which philosophical camp you belong to. And the power of this one simple axiom just ripples outward. It helps in proving other complex mathematical theorems. It even connects to some really deep philosophical and theological ideas about unity, suggesting that the collection of all possible sets could be a genuine unified entity. But most importantly, it just hardens the entire foundation of set theory against the corrosive power of paradox. So it's a fascinating takeaway, isn't it? The universal language of math, something we think of as pure, cold logic, needed an explicit new rule just to save it from a self-referential paradox. And that leaves us with a final thought. What unspoken, implicit rules govern our own day-to-day thinking? And what happens if they too have a loophole?